next up, a beast and a poodle celebrating SWEET32 by Bojan.
Righty, so welcome everyone. How do you scare people from a presentation? Put crypto in the title and everyone will run away. Well, it's not in the title, but it's in the description, so I might have done this a little bit more stealthy, but okay. Hello everyone. It's my great pleasure to be here again this year. My name is Bojan, and for the next 60 minutes or a little bit less, I will be talking about some crypto vulnerabilities. And my goal today, yes, I'm looking forward to it, at least me. And my goal today, I would be the happiest man today if everyone in the room understands how the POODLE vulnerability works once we get out. If you don't, we always have a rakia party, right? So after, a couple of glasses of rakia, everyone will understand crypto. Just a little bit about myself. So I'm second year here in Balkan. I'm originally from Croatia, where I lead the penetration testing team in a company called Infigo. I'm also a SENS instructor, so I teach the SEC 542 course, which is Web Application Penetration Testing and Ethical Hacking, a long name of a course. I used to teach one other course, 504 as well, but I like this one more. So if you want to know more about some of the SENS stuff, just let me know. I'm also one of the SENS Internet Storm Center handlers. If this website is not in your bookmarks, that's perfectly okay. But there is one cool thing that Johannes, who is the main guy behind the Storm Center, does every single day, and that is the daily Stormcast, or a podcast that he publishes every single day for the last 10 years. Every single day, except for weekends, so every working day. So it's a really, really cool podcast, only 10 minutes long, something like that. And every single day he posts about new things. So this is something I like to listen to when I commute to work. I just download the latest version, only 10 minutes, right? 7 to 10 minutes. And it's about latest things in security in the world, I don't know, attacks, incidents, and stuff like that. So it's a good thing to listen to. So why did I come up with this presentation? Well, to be honest, I got really, really tired about seeing something like this. Since I do penetration testing all the time, I sometimes see some other reports as well. I sometimes see reports from tools. And quite often I actually see that people try to rank how severe a certain vulnerability is. And sometimes I see something like this, where a certain vulnerability called SWEET32 has been ranked as a high-risk vulnerability. And this actually bothered me so much that I decided to spend a lot of time into reading and figuring out how different vulnerabilities work, so we can actually correctly assess the risk that is resulting from these vulnerabilities. I know at least one person in the room will like this, who probably takes a look at a lot of reports, sitting over there, incognito today, not in a suit. The goal of my presentation today will be to cover some of the most commonly reported and most commonly seen crypto-related vulnerabilities, basically SSL and TLS vulnerabilities, and I will try to demo the POODLE vulnerability on a real system. So hopefully it will work. With live demos, you never know. It depends if you prayed enough to the demo gods. If they are happy, then everything will work. If not, things won't. So we will actually see, but yeah, let's go on. Okay, so as I said, I will discuss some of the most common SSL and TLS vulnerabilities that are reported either by penetration testers or sometimes by tools when you simply scan the networks. You can see some of the names here, and I'm pretty sure that a lot of you heard about most of these, if not all of them. It's almost customary to have those, I call them celebrity vulnerabilities. So they have like a cool name, they have their own domain, and a cool logo. That's something that a celebrity vulnerability must have. And some of these are definitely celebrity vulnerabilities, but we'll see how viable their exploitation really is. We will see what are the requirements, and if, for example, can someone attack you with a POODLE vulnerability while you are using the Balkan wireless over here. Is anyone using the wireless actually? No one trusts the wireless here, right? Yeah. Me neither, yeah. So we're safe, yeah, just unplug it. Okay, so before talking about how this actually works, and there will be a little bit of crypto here, but you don't need to have any prerequisites to understand what I will talk about today. The only thing you need to know is how XOR actually works. I'll have a slide about that just to refresh your memory, but it's the only thing you will need to know. And a little bit of concentration. So the main goal of SSL and TLS is to enable private communication over insecure communication channels, whatever they are. We use it every single day. We actually cannot live without TLS today. I keep saying SSL all the time. I guess that's because I'm an old-timer, but I should be talking about TLS these days. So there are three important parts about TLS that you can see here. The first one is key exchange and authentication algorithms. So when you connect to a website, for example, to Facebook or Gmail or whatever is the TLS website that you are connecting to, in the first step, you first authenticate the remote party. We do that via certificates, so everyone knows about pop-ups that you get that you should obviously not click on, but people do, because the pop-up actually performs the first part, which is the authentication part of the remote endpoint. In this particular part of the negotiation, there is also key exchange, and two sides have to define which encryption algorithm they will use in order to encrypt the rest of the data that is being exchanged. So the key exchange part happens with uses the asymmetric cryptography, which is slow. So we cannot use it today. Even though we have really, really fast CPUs, it's still unbelievably slow. So when you connect to Netflix to stream your latest video, and it's going over SSL or HTTPS, after the key exchange part, we actually switch to one of the symmetric encryption algorithms here that are fast. So we can allow a lot of data to be encrypted with them. So typically today, either SSL or AES are used as the most common symmetric encryption algorithms. Very rarely I still see RC4 somewhere. People consider it to be bad. We'll see why. And there is a new algorithm that you can see here called Cha-Cha that Google is pushing a lot. So Google is trying to push Cha-Cha a lot with Google Chrome. There was another algorithm which was kind of similar called Salsa 20. So you can see that the author of this encryption algorithm is obviously a passionate dancer, I guess. Maybe Tonimir knows him, or maybe Tonimir is that guy. What? DJB, yes. But he likes dance names. And finally, we have message authentication. I'll explain how this all works, and I'll hopefully have some pictures as well to show that to you. So, as I said, these two are the most common symmetric encryption algorithms today, but by only choosing a symmetric encryption algorithm, there is still another thing that we have to select, and that is the cipher mode that we want our encryption algorithm to work in. Now, if anyone is a developer here, typically when by default you select, for example, AES or SSL, by default, the mode that your algorithm is working on will be the first one, electronic codebook. With electronic codebook, there are certain issues that I will show on the next slide. So what we will actually talk about throughout this presentation will be the second mode, cipher block chaining, CBC, which is really the cause of almost every issue that I will talk about today. Just a little bit about the first mode, electronic codebook. You can see here why that particular encryption mode is bad. So this is a bitmap image on the left side, which has been encrypted with AES 256, which is like the strongest encryption algorithm that we use today, with a really, really long key. And on the right side, you can see that content being encrypted. So pretty obvious what's encrypted, right? Why do we actually get this? We get this because for every single block that we encrypt with the ECB, electronic codebook mode, every single block will have the same output when we use the same key. Obviously, we have a lot of same content around here, so that content will preserve the pattern which means that in the image on the right side, we can see the pattern of the original image, even though it is strongly encrypted. So depending on what you encrypt, this mode might not be the best thing to choose. That's why a lot of developers actually pick the second mode, which is CBC. But before diving into that, just a quick refresher about the XOR operation, which is the root cause of all the issues today. So just to remind you about how XOR works, I'm sure everyone knows here about XOR. So A XOR B is B XOR A. We can switch sides easily, so A XOR B equals C, A will be equal B XOR C, A XOR 0 will be A, and A XOR A will be 0. So this is all you need to know in order to understand how we will exploit the POODLE vulnerability that hopefully I will also demonstrate successfully. We'll see about that when it comes there. Another thing that we need to know about symmetric algorithms, at least those that were on the left side on the slide, so DES, triple DES, and AES, these are so-called block symmetric encryption algorithms. In other words, whenever you encrypt something with AES, your content, your plain text, must first be divided into blocks. And then those blocks will be encrypted into the resulting ciphertext. Those blocks are 8 bytes of size for DES and triple DES, and 16 bytes of size for AES. We cannot change that. That's how the algorithm works. So when you want to encrypt a sentence, which is, for example, 30 bytes long, and you want to use AES, the resulting encrypted output will be 2 blocks long, which is 32 bytes. 2 blocks of 16 bytes. It always has to be a multiple of a block size. So if you remember the previous image here, where we preserved the pattern in the original image, CBC, cipher block chaining mode, was an attempt to actually break that pattern. So when you take the same image and you encrypt this image with the AES 256 encryption algorithm in the CBC mode, you will actually get something like pure noise. There is no pattern anymore. And here you can see why. The main reason is that every plain text block will have some kind of a feedback from the previous block, and that feedback will be used as input for an XOR operation before encrypting the content. So here, let's see if this works. Yeah. Over here you can see my plain text on the second block, and before actually encrypting my plain text, I will be performing an XOR between my plain text block and with the output of encryption of the previous block. So by performing this XOR function, we are actually breaking the pattern. And now we'll get pure randomness when we encrypt some data. Obviously, we have a problem with the first block, right? What do you feed to the first block? There is nothing from the previous block. So that's why we have the IV, initialization vector. And the IV is simply 8, in this particular example I'm using triple DES here, so I have blocks of 8 bytes. It is simply 8 random bytes that we need to use to perform the XOR operation with the first block before being encrypted. And those 8 bytes are actually sent in plain text. We don't care about them. We just use them as the IV. So this is how encryption works. Let's see how decryption works. It's actually very cute when you look at it. So let's take a look at the second block, for example, again. So we have the ciphertext. We decrypt the second block. And now in order to get the original plain text, we have to again perform the XOR operation with the contents of the previously encrypted block. So if I go back one slide, just take a look at the second block, right? So see what the image looks like. When I quickly flip between them, you can see what's happening here. So we take the contents of the second block, decrypt, but before getting the plain text, we need to perform an XOR operation. This will be the doom of everything, that XOR operation. All good? If you have questions with this, ask me right now, because by the end of the presentation you will forget about this and you will not understand how it works. So any questions, please shoot them right now. It will be the best, most beneficial for everyone. So let's see what an HTTP request looks like Sorry, there's a question? Yes. Well, how else will you give it to the other party? You could maybe derive it from a key, but basically it doesn't really matter. Those 8 bytes, those 8 random bytes, you will perform the XOR operation. So even if the attacker, who can maybe sniff on your traffic, even if the attacker sees those 8 bytes, they will not help him or her to actually decrypt the data. So we are okay with sending that in plain text. You are right about other possibilities. We could maybe derive it from the encryption key or something like that. We could do that, yeah. Okay, so let's take a look at what an HTTP request looks like before it's being encrypted by your browser. So when you open Facebook or Gmail or whatever you want, and in your URL bar, you type in gmail.com, and let's say that you have already logged into Gmail. You know that Gmail stores the cookies in your browser. So when you close your browser, when you open it, you are still logged into Gmail, right? That's how they know who you are. So when you type in gmail.com, your browser will issue a GET request, a get/HTTP11 request to the host mail.google.com, and it will supply the session cookie. I have a very simple example here where I performed a GET request to the isc.sens.edu website, and I already have a PHP session cookie here. Now remember what we have to do with block ciphers. We have to split our input into blocks. So if I'm using TripleDES here, what I will do is split my message, my GET request, into 8-byte blocks, and this is what I will end up with. So I have a typical HTTP 1.1 request here. I have the host header, which tells the server which web page I want to retrieve, and I have a session cookie here. There are many other headers that our browsers will send, but for the example, I'm just using one because this will help, hopefully, everyone understand how this works. And as I said, if not, there is always Rakia, which can help you with understanding. And at the end, we will have carriage return line feed. So we have \r/n. Now, check what happened here. I deliberately picked this particular request. So the last block, I have 4 extra bytes. Now, before encrypting this data, there is another thing that must be done. We have to calculate the message integrity checksum, and that message integrity checksum will be appended to the message before, this is very important, before encrypting the message. Now, let's say that in this example, as message integrity, we use SHA-1. SHA-1 will produce contents of 160 bits, which is 20 bytes. And I deliberately picked this particular message, so when you append the message integrity checksum, which is 20 bytes, you will see here that we end up with what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 full blocks of message. Now this message must be encrypted. That's what SSL or TLS does when you serve to a certain web page. But there is another thing that we must be aware of. When I go back here, notice that we had 4 extra bytes, which means that to the receiving party, I somehow must tell that there are 4 extra bytes, right? When you decrypt this, when you decrypt all contents, those last 4 bytes will probably be some kind of garbage, depending on what I put into those 4 bytes initially. I can put, for example, 4 zeros, but what if I actually want to encrypt zeros? How do I tell the receiving party, hey, those last 4 bytes, you are actually supposed to discard them. They are just garbage because we are using a block cipher. So the protocol says that in order to signal to the receiving party how many bytes the receiving party has to discard, you will actually put in the very last byte the number of bytes that need to be discarded. Okay, that's the protocol. So in other words, if I wanted to send this particular message here, the actual value in the very last byte, in this byte here, would be 3. Because that tells the recipient that 3 bytes besides the last one should be dropped. There are 4 bytes of garbage. Now, the protocol also says you always have to have so-called padding. This is called padding. So even if you have perfectly aligned block, right, the receiving side must know how many bytes to discard. So how do we do that? We actually append a full block that will have 7 bytes of garbage, and the last byte will have the value of 7. So when the recipient decrypts the last block, the recipient will see, oh, the number is 7, so I discard 7 bytes before this, and it will all work perfectly. Still all good? Okay, so the last byte will tell, yes?
So we always need to have some garbage.
Exactly, you always need to have padding. They call it padding, so garbage is not maybe nice for a standard, but you're absolutely right. We always have to have some garbage, which will be padding here. Now, in SSL version 3, the content of these 7 bytes doesn't matter. So we can have 7 bytes of full garbage, but the last byte must have the value of 7, right? This will tell the recipient that we discard the whole last block, and then we have the other part of the message that will be correctly used. So this is the attack idea. Yes, another question. Excellent.
Do you have, for example, that one padding that says 0?
0, no.
So
It must be 1 is minimum and 7. So depending on how many, you always have to have 1 byte which is padding, the last one, right? And then if you put 0, then you don't know if it's 0 or what you need to do. So always have to have either a full block or it will be 1 to 7. So values 1 to 7. Right? Yes, there is a range. So for example, if it's 4, then we discard 4 bytes before this, and then we have the rest of the message. Alrighty, so this is the idea for attack. Let's say that the attacker successfully performed a man-in-the-middle attack against us. So that is one of the prerequisites for this attack. We need to be able to perform man-in-the-middle. How difficult is it to do man-in-the-middle today? I don't know. Exactly. So it's actually pretty difficult unless you are on Wi-Fi. So maybe if you connected to the Balkan Wi-Fi, maybe some of these guys here, the one over there, they might be running some man-in-the-middle attacks and sniffing your traffic. So this is prerequisite number 1. The attacker must be able to see your traffic. Then the biggest issue in SSL version 3, which is the POODLE vulnerability, is the following fact. When the server decrypts the message, if the value of the last byte was, for example, incorrect, so it was 10, it cannot be 10, it can be 1 to 7, because we have 8 byte blocks, right? If the value of the last block, of the last byte in the last block is 10, which is an invalid value, then the server will actually send an SSL signaling message on the wire to the sender, telling the sender, hey, decryption failed. Okay? So this is called an oracle. In other words, if I can very, very cleverly juggle packets or blocks around, I might be able to make the server tell me when something has been decrypted correctly and when it hasn't been decrypted correctly. Because if it hasn't been decrypted correctly, I'll see the signaling message, which will say, hey, decryption failed. You'll understand this in a second. Just wait. Just stay with me for another few slides. So this is what the attacker will do. Let's say that we want to decrypt the contents of the second block for some reason. We can decrypt all of them, but let's say for this example we want to decrypt the contents of the second block. So the attacker, who has already launched a man-in-the-middle attack against all of us here, the attacker is monitoring our traffic, our encrypted traffic. SSL traffic can be decrypted easily. And what the attacker will do, since he can perform block juggling, packet juggling due to the man-in-the-middle attack, the attacker will take the contents of the block, second block here, and copy, literally copy, that whole block to the last block in our message. Why last? Remember that 1 byte. That 1 byte will be very, very crucial. So the attacker literally takes the contents of the block and copies to the last one. Nothing else. Right? Now, what will happen? Since the attacker blindly copied the block to the last block, when the server decrypts the message, the first thing that the server will do is check the value of the last byte. If the last byte is anything other than 1 to 7, it's immediately an error, right? It cannot be. It cannot be anything else but 1 to 7. So if it's like 52, it's an error, and this is the message that is being sent. So this is, I call this with Wireshark, and you can see here, this is SSL or TLS alert 21, which says decryption failed. Now, let me just go back here quickly. Remember the message integrity part, those 20 bytes that were calculated in order to preserve the integrity of the message, right? If, for example, the value of the last byte decrypted to 5, what will happen? The server will discard 5 bytes in front of the last one, then it will take the next 20 bytes, thinking that this is the integrity checksum, the SHA-1 result. But it is not, because if we discard 5 bytes here, we have these 2 bytes which are garbage, right? It will try to calculate the integrity hash, it will fail again, and guess what will happen? The same message will be sent, right? So now, the only case when this will actually work is when the attacker copies the block to the last one, and the attacker gets so lucky that the last byte actually accidentally decrypts to value 7. If the last byte decrypted to level 7, value 7, then the attacker can actually calculate the value of that original byte thanks to the XOR operation. So let me show this for you, and this is the most difficult part of the presentation. After this I have Beast, which I suggest that you try to understand only after a bottle of rakia, right? This is like half bottle. This is more complicated. So this is why the whole story actually works, and this is the most complicated part of the presentation. So at the top you have the encryption process, CBC encryption process. At the bottom you have decryption. I want to steal contents of the second block, the one originally highlighted in green. See it here, plain text. That's the one I want to steal. So this one will be encrypted after performing XOR with the yellow block into the red one. What the attacker does is copy that block to the last block in the message. All good so far? Right? I repeated this like 10 times, so I think it is. So he just copies the value of the block. Now, let's see what happens. This block here, the red one, when we decrypt the red one, right? And when we XOR the red one with the purple block, which is the one next to the last one, we actually get what? We'll get the green block. Why? Because, well, that was what originally was there. So we can see that the green block is decrypted last block XOR previous one. So all we're going to do now is just extend this a little bit so we'll see why it works. Now, what is my plain text block here, the last one? If the decryption was successful, right? Remember, if the decryption was successful, if and only if, the value of the last byte will be 7. That's the only case when the decryption can work. Why? Because the attacker took the second block, copied it to the last one. When it gets decrypted, any value other than 1 to 7, immediate error. If it's 1 to 6, it will drop garbage, and the message integrity will be incorrect. So the only way for this to work is for the last byte to have the value of 7, which means that the contents of the last block will be dropped. We will calculate the message integrity hash, which will be correct. Why? This is why. I will drop the last block, right? Everything else remains the same. And this will hold true. So for that one request, and I will explain how we send requests, for that one request that succeeds, the attacker knows that the last byte of the last block was 7. It cannot be anything else. So this will hold true. We have 7 bytes of garbage. We don't know about them. We don't care about them. 7 will be again the first equation here, right? Makes sense. That's just what we decrypted the contents to. Now, thanks to XOR, you just switch sides. So I move the block with garbage and 7 to the right side. I move the decryption of red block to the left side. So this is all cool, thanks to XOR. And now, how do I get this? How do I decrypt the red block? Well, originally, the red block encrypted is actually plain text, the original plain text block, XOR yellow block. The yellow block is ciphertext, which means that the attacker that is monitoring the network, he knows about the yellow block as well, because it's encrypted. So check this. Now, these two will hold true as well. The decrypted red block, originally, is plain text block, which is green, XOR the yellow block. And now, finally, what we do is this. I switch sides again, and I know that the decrypted second block will be the yellow block, XOR garbage 7, XOR purple block. The attacker knows everything. So he knows the value of the purple block, he knows the value of the yellow block, because these are encrypted, these are sent normally, and he knows that the last byte is 7. And with this, the attacker can actually decrypt 1 byte. Only 1 byte. We don't decrypt whole block. We encrypt 1 byte at a time. So all I need to do now is somehow make your browser keep on sending requests constantly until two things happen. Until I, as the attacker, am lucky enough, so the last value will be decrypted to 7. And I know that the last value of this green block, which is the one I want to retrieve, is actually something I want. So I can only decrypt the last value of a block, which means that when I make your browser send requests, I have to somehow shift the data 1 byte at a time, right? So if it's always in the second block, the byte I'm decrypting will be the last one. Be good for Rakia, or should I do the live demo? Live demo, right? Okay, Rakia later. Or okay, if you still don't understand it, I'll show you the live demo, and then we'll have some Rakia later, and I'll explain that to you. It's a little bit difficult. Yes.
Statistics is like every 7th time you will have this 7.
Now statistics is very, very difficult beast. Definitely not my area. But when you run this attack, you will, on average, need to send about 256 requests in order to get lucky enough to get 7. So on average, it's 256, something like that. Now when I run the demo, we'll see. Maybe I will be completely unlucky, and I will need to send like 5,000 requests to get lucky, so the last byte is 7. Maybe I'll send only 50. We'll see. But in average is 256. So this is the POODLE vulnerability. Notice the requirements here. The attacker needs to be able to perform a man-in-the-middle attack. I must be able to see your traffic. I must be able to actively copy those blocks, right, in order to decrypt something. I also somehow must make your browser send requests. How do I do that? That's not an easy thing to do. So what an attacker normally would do is sniff your traffic constantly, and when they see that you access one website which is not over SSL, which is plain text HTTP, they inject JavaScript into your plain text content. And that JavaScript actually makes your browser keep on sending requests. How about I show that in a real demo? So this demo that I will show to you now has a very simple mock-up web application that is obviously will be abused to demo the POODLE vulnerability. This is what I will be sending. So I will want to steal the contents of the cookie, which is PHP session ID. And by injecting this dummy content, so /AAA and BBB in the body, what I'm doing with this is by carefully injecting this, I will be shifting the plain text contents. So the byte I want to steal will be the last byte in a certain block, right? That's how I shift the contents to get the data out. If you want to do this at home, this is something that you can do at home, right? Not those bad things. Everything is on my GitHub webpage. The original exploit is from this French researcher, I didn't manage to find the guy's name. He's like totally incognito. I had to modify the exploit a little bit. And everything is on my GitHub with the presentation. So you can download everything, go through this. If you didn't understand it, try to redo the demo. So what I will be using here is Ubuntu 14. Why? Because it supports SSL version 3 out of box, so we don't worry about that. I'll be using Mozilla Firefox 30. Again, it supports SSL version 3 out of box, so I don't need to change anything with configuration. So let's do that. Yes, maybe it'll work. Okay, so what I have here is a Windows VM. This is the latest Windows 10, fully patched. Doesn't matter really. This is a vulnerability in the SSL engine. And I have Mozilla Firefox here. And over here, provided I can log in correctly, I will run my exploit. So as I said, typically the attacker would perform a man-in-the-middle attack in order to be able to see our traffic and modify it. Since I have two VMs here, I didn't want to bother with performing man-in-the-middle. So I actually set up my exploit to listen on port 4443, but it's actually just transparently redirecting everything to localhost 443. So I'm kind of simulating man-in-the-middle. It would work absolutely the same. If you want, just use ettercap or bettercap or whatever to do it. All right. Yes, I need a proper IP address, which is apparently 131, which is okay. Scared me initially. So now I'll go to 131 and let's see. 146, sorry, my bad. Alrighty, of course, the pop-up, because I didn't bother about the certificate, so we will do as any other user will do, just click on OK and proceed, because that's fine. And here we have a very, very simple test application that's probably used by some presidents in the world. You know, when I think about nuclear weapon launch websites, they probably look like this. They are from, what, 1990s, right? So what I will do here is I will log in with a password, and there is an SSL error, doesn't matter, I'll try again because that's what a user would do. And okay, here we go. So in a real world attack, the attacker will probably run JavaScript automatically to send requests. I didn't do that here automatically, so I will just click on these buttons here to show to you what will happen. But let me go back to the exploit, and you can see here that we are seeing some network traffic. That's okay. At this point in time, we are just relaying traffic. We don't do anything to it. We are just monitoring the traffic. So since I don't know which particular encryption protocol, encryption algorithm was picked, was it DES or triple DES or AES, I need to first figure out what exactly my browser picked. So I can do a search here, and now the attacker would automatically just run this JavaScript here. This JavaScript just sends a request, nothing specific behind this. Then I go back, I need to send one more, sorry. Apparently didn't click, or maybe I did. There we go. So you can see that we figured out, okay, you're dealing with a block size of 8. So now the exploit knows that when it copies the blocks, they are 8 bytes long, and the last value must be 7. If it was AES, the story would be exactly the same, but the last value must be 15, right? Exactly the same. Exactly. So the same thing. Now I can activate my attack, and now the following thing will happen. When I click here to launch a test missile, of course, what else? Now my browser started sending requests like crazy. And over here, oh, actually we got already lucky, so we guessed one. Over here you can see that we are seeing some requests. For every single request, what we're doing is taking block number 50, see here, block number 50, and copying block number 50 to the very last block. That's the only thing we're doing. And then we're monitoring the response traffic. When we see the SSL alert 21, we note that decryption failed. If we don't see that, then we know decryption succeeded. And thanks to the XOR, we can calculate the value. So we guessed another another byte there. Let me show to you what the browser is doing. I will open developer console, and you can see here what's going on in real time in the background. I'm constantly sending post requests, which are basically garbage, right? I don't care about them. I just want the 1 byte that I actually need to decrypt to be copied to the last one and the last value to the 7. That's what I want to happen. And I keep on sending this constantly just until I get lucky enough to decrypt 1 value. So we guessed actually 1 more character over there. If you want to see that I'm not actually lying, I will go to console here, provided my Firefox wakes up. I will just zoom a little bit and I will do document.cookie, and you can see the cookie here and see the value. So it's 7RIOV. When we go back here, that's what we actually successfully extracted. So if I just leave this running, in some time we'll actually end up extracting the value of the cookie, and that's all I need in order to take over your Gmail account or Facebook or whatever I want. And this is actually how POODLE works. So by looking at this, one thing that I'll kill this. One thing that I thought about when going through the vulnerabilities was that POODLE is a real one, right? So even though there is a number of prerequisites that an attacker must fulfill, like man in the middle, be able to make your browser keep on sending requests, they are not impossible, right? They can happen, especially if you're connected to wireless. If you accidentally, in second tab, open a non-SSL website, then I can inject JavaScript into your session. So this, I would say, is actually a real attack. Beast is another commonly reported vulnerability, one that I will definitely not try explaining right now. You'll see why here. This is why. See this on the right side? Way more complicated than before, and need way more rakia for this, as I said. But with Beast, the difference is that we are actually exploiting the browser. So in the first case, it was the server telling us that something is wrong by sending the SSL alert message, which says decryption failed. With Beast, we actually see that message from the browser. So we kind of changed our targets. Now, this actually happens because the way the browsers work, when you need to encrypt a lot of data, browsers will actually keep on reusing some of the crypto material from the initially established session. That's why Beast is possible. As I said, I will not dive into explaining this right now, but what I will tell you about Beast is that the prerequisites are the same. So the attacker needs to be able to run man in the middle. The attacker needs to be able to run JavaScript in a browser to keep on sending requests. But the way to fix Beast is to simply upgrade your browsers. So that's quite easier. Now, crime is one of my favorite vulnerabilities because it's so easy to explain. So if you didn't understand POODLE, you will understand crime for sure, and you'll love this vulnerability. It's so subtle, it's actually so cute. So crime is a vulnerability that uses compression as out-of-band channel to tell the attacker on what's actually being encrypted. Or in this case, compressed, because SSL and TLS compress data as well. Now, the latest versions don't, but previously, when crime was actually abused, we did compress data with SSL. Now, the reason why we can exploit crime, is because compressed data will have certain length. Let me demo that to you. There'll be another live demo, but this one will work for sure. I was lucky with the last one as well. So I'm going to use Python here, and I will import the zlib library. I will just use this as a simple example of why compression can be abused here. Now, this is a bit more complicated in SSL, but this will allow you to explain, to understand how it works. So let's say that here I have my request, HTTP 11, then I have /n, host will be, I don't know, balcon.org, and then I have my PHP session ID cookie, which will be something like this. Okay, long enough. So now, as the first step, let's compress this and let's see what will be the length of this. So length of compress of A is 72 bytes. All right, now the attacker wants to find the contents of the PHP session ID cookie, because once I steal your cookie, I become you. That's how web applications work. This is my prime target. So I, again, must be able to run man in the middle. I must be able to make your browser send requests, but check which requests. The attacker modifies the request, so here in the parameter, he does something like this. So he adds the name of the cookie that he wants to steal. How does he know that? Well, he just checks his own session. The attacker doesn't know what is the value of the cookie, so he tries to guess 1. Right? We just try to guess first byte. Let's compress this. 76 bytes. Fair enough. So the attacker tries with 2. 76 bytes. Fair enough. The attacker brute forces everything, finally tries with A. Notice that A is actually the real value of the first byte of the session cookie. What's the compressed value? Oh, 75. So I know that the value of the first character is actually A. So he goes to the second, right? Again, he doesn't know. He tries with 1. What's the value? 76. He tries with what? S is the second one? S. Oh, it's 75 again. Because thanks to compression, the size will not be increased. And the attacker just keeps on using this to brute force every single character. Notice that he only has to guess 1 character at a time, so this is really, really doable. That's how crime works. Very, very simply explained. It's actually a bit more difficult, but this is how it works. So these are the requirements. Again, as I said, man in the middle, JavaScript, and so on. As you notice by now, all the requirements are the same, right? Always man in the middle. Always must be able to run JavaScript in your browser, because I want to make the victim's browser keep on sending requests. What else do we have? RC4. So RC4, a lot of research was done. I know everyone heard about RC4, how bad it is. But besides being used in web, which was a really bad implementation as well, these two researchers in 2015 found that there are a lot of biases in RC4. So that's why RC4 is bad. If I send a lot of traffic and I encrypt that with RC4, there are some biases, which means I can actually figure out what data has been encrypted. So in order to launch that attack, can you guess the requirements? I need to run man in the middle. I need to be able to send your browser, to make your browser send a lot of data. And once I do that, I can actually try to figure out certain parts of encrypted content. So these two guys found out that if they encrypt 300 gigabytes of data, 300 gigabytes of data, they can decrypt 16 bytes of data. Right? So they can steal kind of your session cookie maybe, but they need to encrypt 300 gigabytes of data. Now, in 2015, when you told sometime I need you to send 300 gigabytes of data there, everyone would say, no way. I mean, who can send 300 gigs of data? Today, not that impossible, right? We have fast links. We can do that maybe not easily, but easier. And remember one thing, with crypto attacks, they only get better with time. Finally, SWEET32, just quickly, because I have only like 2 minutes left. Again, a crypto issue. With SWEET32, what we do is we are actually exploiting the birthday attack. Anyone knows what is the birthday attack? The birthday attack says that in a room of 23 people, we have a chance, 50% chance of 2 persons sharing the same birthday. So we probably have someone here who shared the same birthday. Well, 50% of probability. And thanks to this, if we encrypt a lot of data again, then if we use 64-bit encryption algorithms, we have more than 50% chance of 2 blocks being the same, 2 encrypted blocks. When 2 encrypted blocks are the same, I can actually get the plain text context. But in order to do this, again, I need to check how many? A lot of requests, right? I again need to send gigabytes, hundreds of gigabytes of data to make that collision happen. Same prerequisites, man in the middle, send a lot of traffic, actually send how much? 300 gigs of traffic again. But notice what happened in 2016. These guys did it in only 30 hours. They were better than those in 2015. It took them less time to send 300 gigabytes of data with a browser. Again, remember this, crypto attacks only get better with time. So, just to finish quickly, if you want to test any of the websites that are your own or in your own engagements, there are a couple of tools that you can use. I personally prefer to use Nmap. Nmap has a really, really nice script called SSL enum ciphers that I use to enumerate the supported encryption algorithms. Fantastic script, you can run it wherever you want, and very, very easy to do. There is another utility called testssl.sh. Again, open source utility that you can use. It will nicely display everything that is supported, and it will indicate what are the problems here. I would just like to draw your attention to one thing. The SSL enum cipher script in Nmap does not support SSL version 2 not by default, but at all. So if you're scanning supported protocols and you want to check if your target server supports SSL version 2, you need to run a specific script called SSL version 2. The SSL enum cipher script will not support that. TestSSL.sh I already mentioned. And finally, Qualys. You can use Qualys as well. They have a really great public site that will allow you to enumerate supported encryption algorithms. Just make sure that you select this option over there. Do not show results on the boards, because otherwise when you scan your own website, it will be publicly displayed on Qualys website for a certain amount of time, which is probably something you don't want. And if you use this, then you'll see a report such as this one, which will say, hey, you've done a very good job. You get an A+ for configuring the SSL TLS settings on your websites. Apparently, the guys from the SANS did a good job over there, or whoever is the provider they're actually using. And as a conclusion, my, let's say, conclusion based on some research I did would be that POODLE is absolutely a real threat. So SSL version 3 should be disabled. It can be exploited, especially with browsers. With proprietary protocols, it should still be okay. Why? I cannot make the source repeatedly send the traffic. That's why the PCI DSS industry allows SSL version 3 for point-of-sale devices. When you pay with your credit cards, those devices might still be using SSL version 3. They are vulnerable to POODLE, but it cannot be exploited, at least with knowledge we know right now. Crime and Beast should be fixed just by upgrading browsers. RC4, again, real threat, disable it. SWEET32, in my opinion, probably informational vulnerability. We can live with it for a while. And again, another time I'll repeat this, keep in mind that crypto attacks only get better with time. And with this, I hope I didn't kill you with crypto talks. I hope you still have strength for remaining presentations, Rakia and whatnot. If there are questions, I'm not sure how much time we have. We have a few minutes, like only 2 minutes, or I can take them outside. I'll be here till Sunday, so please feel free to flood me with questions or whatever. Everyone is crypto dead. That gives us enough time for the next presentation. So thank you everyone again. Thank you.